So, having seen various methods to estimate parameters with generalized linear mixed models, PQL, MQL, Laplace, the numerical integration methods, the question is, what can we now do in practice? Well, there is glimix and there is NLmix. These are the two key procedures to use in this context. Glimix can be used, for example, for PQL and MQL, as the title says, but we should add, and that's also what's illustrated, it also does Gaussian quadrature. So you obtain PQL, you obtain MQL if you change the method is to these funny options. I'll explain that in a moment, but I think one of the preferred methods now is the Gaussian quadrature methods. If you change this to Laplace, method is Laplace, then you have the Laplace approximation. Other than that, we have seen this model more or less equal forms or different forms repeatedly, but onychomycosis response here is modeled as a function of treatment by time interaction. Distribution is binary, and unlike in the marginal model, we now have random intercept rather than random underscore residual underscore. Subject is ID number is still there. Now, why this RSPL, RMPL? Let's ascribe it for the time being to SAS, but the R can be replaced by an M also, and that's the difference between what we could call the maximum likelihood is version and the restricted maximum likelihood is version. If you ask the question, which of the two should you use, I'd say none of the two, of course. One is a small correction versus the other, but we have seen just how poor PQL and MQL may perform. So why would we worry too much about improving a method that actually functions very poorly in the first place? So I would not worry about that too much. Would I ever use PQL? Well, sometimes to get starting values. To save somewhat on the cost of, let's say, having totally arbitrary starting values, then PQL may still provide you with somewhat more reasonable starting values. Well, the output is always the same. You get your covariance parameters, you get your fixed effects. We know how to interpret that in the meantime. And then NL mixed. NL mixed is of a different nature, because NL mixed really is what the name suggests. We always have to be careful with it, but a procedure for nonlinear mixed effects models. Now, nonlinear mixed models, unlike linear and generalized linear mixed models, have no prescribed linearity left. Anything goes. It can really be anything at all, which means that you cannot really pre-program all this much as a programmer. You need to have an open programming tool available. For example, if we go through the motions, we know the model in the meantime. This one, what I'm circling here, this theta, is nothing but the linear predictor, including the fixed effects, the covariates, and the random effects. Then we take the exp of that, and then the exp divided by 1 plus the x, that's the probability, and bingo, that is what's specifying my model. The model is of binary type. That I know because that's what I'm specifying. And then one of the parameters is declared a random effect here, and we do that by giving it a normal distribution with mean 0 and variance, standard deviation sigma and variance sigma square. Subject is ID number, shouldn't be forgotten. But then we say, hey, wait a minute, sometimes we have seen it prior to a slash in certain procedures, then we saw it after a slash in other procedures, and here there is not even a slash. What is that? Well, the slash here is reserved for exactly its purpose in mathematics, that is division. Where to put it, don't think about it, just place it in accordance with the syntactic rules, and that can be different sometimes for no apparent reason in one procedure versus another. Okay. The other question is, how does SAS know which are parameters? Because if we look at the output, we dutifully get the 5 parameters that we wanted, the 4 betas and then sigma, and if you really want, sigma square. Well, you could say it's obvious. You have the parm statement. Wrong, because the parm statement does not need to be defined. And it's possible, if you define it, if you include it, that not all parameters are given starting values. So it doesn't help SAS all that much, especially not when it's not there. So SAS looks at all of your programming code. And it actually continues also here. So I'll do it again and say SAS looks at all of your programming code. And wherever you introduce something, it tries to work out what it is. So data is defined. It's a quantity that's defined. Beta 0 is not a reserved word. It comes out of nothing. It's not a column in the data set, so it must be a parameter. Be the same, but then later it's defined a random effect, so that's safe. Beta 1 is a parameter. Treat n, it goes look in the data set, it sees there is a column treat n, it knows it has to use that x variable rather than considering it a parameter. But just imagine I had made a typo and the treat n would have been written as treat. SAS wouldn't find it in the data set and think this is a model where two parameters are multiplied, beta 1 times treat. Well, it's not going to work, of course, they're not distinguishable, they would jointly be aliased with the intercept, this would be a big mess. So you have to be extremely careful about your model formulation. And then it goes through the rest, and it doesn't find any parameters anymore, because every time, yes, it does here, but not on the next lines, until it gets here, where it finds a sigma that it hasn't seen before, and yes, there we go. Okay. Now, the method is actually relatively simple. We have a model that is an extension of the linear mixed model, starting from the exponential family, GLMIDs, including random effects, normally distributed. You have a likelihood function. Yes, it involves an integration, but other than that, it's standard likelihood inference. Yes, but this likelihood may be much slower to maximize, and also it sometimes suffers from issues with starting values, because the likelihood can be very hard to get to converge. You need to have patience really in this context. If you'd like to do random slopes, you could do that. You could have beta 1 and then beta 2 times time here, and then that pair of random effects is given a normal distribution with mean 0, 0, mean vector 0, 0, and variance covariance matrix D11, D12, D22. And you see that SAS specifies only the 3 non-redundant elements. It knows that this needs to be D12 as well, of course. Okay, so a few comments, and some of these have to be expanded. There are different optimization methods. Yeah, am I referring to the numerical integration? No, I'm not. There is that, but there is also Newton-Raphson, Fisher scoring, and also various alternatives also. If it doesn't work, try another method also. You can include constraints. You can, for example, say sigma square should be greater than 0 or should be greater than or equal to 0. You can do that, but wherever possible, I try to do that with defensive programming. So if you specify a standard deviation, you square it, there is no problem. You're always going to have a variance that is positive. So even if a standard deviation is -7, the variance will come out 49, and that's fine. Is that -7 not a problem? No, because the only parameter you interpret is the variance, and you know that that -7 really should be +7, of course. For the outcome model, there are several tools available, several choices, normal, binomial, Poisson, etc. But you can also go fully general, and that will be illustrated in the ordinal chapter with the so-called general likelihood, where you not just specify the key parameter in a predefined likelihood. No, 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 no. You define your own likelihood. Full freedom at that stage. You can do empirical Bayes estimates. Random effects need to be normal, but that's not important for us now, because we usually use normal random effects. But even if you want to break that, you can use all sorts of transformations of normal random effects. Simple example, take a random effect, square it, because you can do that, and you get a chi-square distributed variable. Only one random statement to be specified. That is, in more recent versions of SAS expanded, you will be able to use more than one. If you can, choose your own starting values, and you may get them, for example, from PQL, MQL, even from GE, because it may be sometimes a little frustrating to see it diverge with its own specified starting values. Okay. With that in mind, I think we have considered most of what we can do in SAS. In R, you have LME for linear mixed models and LME for nonlinear mixed models, just as a counterpart. And then there is the main statements here that are discussed. I advise you to read that in a bit more detail. But I will say, I will make a few comments here and there. The PARM statement, as I said, it's not necessary, but it's highly recommendable because the default starting values are all equal to 1. SAS doesn't search for them, it doesn't use an algorithm or anything like that, it just plugs in 1 if you're not doing it. Why 1? What's special about the number 1? Why not 0 for that matter? Well, often parameters are variance parameters, standard deviations, variances. If you set them equal to 0, you may be in trouble to begin with because it's on the boundary. So that's why it usually uses 1, but that's not a guarantee for it to work. It's not a guarantee for it to converge, so you may want to do that yourself. Here is the collection of models, as I said. For the random statement, you can specify normal random effects, but as I said a minute ago, by transformation you can definitely generalize that as well. And in the random statement you can include out is EB for empirical Bayes estimates. Okay, that doesn't bring me to the end of models for non-Gaussian longitudinal data, but it does conclude part 3, which was entirely devoted to generalized linear mixed models. And in part 4, as I advertised earlier, we will say, hey, for example, for GE, we went one way. For the generalized linear mixed model, we went another way. And these approaches seem to be totally different from each other. Is there a connection after all? That's the topic of part 4.